artery will more than halve the volume flow rate. So small changes that are preventing flow through a vessel have really dramatic effect on resistance, increasing resistance, and really dramatic impact on fluid flow to that tissue. You can see how it increases up to 80%. So think about it's just wild to think about what sorts of pressures would be required to restore to normal flow rate to accomplish to get rid of that plaque, right? To get rid of, to bypass that. It's just tremendous. So kind of summarizing what we just said about this relationship is, this flow regulation is largely accomplished by vasodilation and vasoconstriction of the smooth muscles that change the radius of the vessels. The smooth muscles, remember, are responsive to calcium, and therefore responsive to all kinds of calcium inhibitors and stimulators, and some of those we've mentioned in the past. The small vessels are really dominant contributors to flow resistance because they are so numerous. And what we just saw is that small amounts of occlusion can really have dramatic impact on blood flow and on health. I wanted to remind you that how the structure links back to this. So we already spent quite a lot of time last time talking about the structure of arteries and veins, but hopefully now you can recognize them in cross-section and in histologies, and to remind you that these arteries are responsive to calcium entry from the extracellular fluid. They're called calcium channels, and that means that neurotransmitters, hormones, many types of paracrine molecules can accomplish changes in radius here. That was from our last time. And in contrast, I wanted to show you again the veins, where the walls are so much thinner than the arteries with much less elastic tissue, and they're able to expand more easily. Because they have less resistance. Kind of this, remember we talked about this stretchy looking balloon, and they're able to accept volume from the arteries. Do you remember what changes the radius of a vein in contrast to the arteries? So we said the arteries are surrounded by smooth muscle, and that's contracting. Do you remember how veins can contract or dilate? What's the approximate cause?
Skeletal muscle.
So skeletal muscle can push and pull on those valves, right? That was one way that we saw. Any other contributions to the veins opening and closing? Yeah. So essentially, yeah.
Respiration.
Respiration, we talked a little bit about that. Yeah, respiratory movements. Yeah, so they're responding to sympathetic signals as well, right? But they are not themselves surrounded by smooth muscle. Okay, so I just spent a whole lot of time talking about Poiseuille's law, and now I'm going to tell you why it's not so accurate. Now that I told you all these great parameters that it can predict and what it can do. So this relationship is really relates to some ideal conditions that are actually not applicable to blood, but it turns out are close enough that we can still use it to get some good approximations. So it's useful, but blood is different in some key ways. So I wanted to point those out to you. So one of those important ways that you might have seen a little note at the bottom is that blood flow is not laminar in most vessels, right? So what does that mean? Can somebody kind of elaborate on that a little bit for us? What does laminar flow mean to you? Smooth flow?
Without like the bubble kind of stuff.
No bubbles. This is absolutely
So I think,
That's good, that's true. It's smooth, it has no bubbles. But, you know, so if I go out to, you know, I don't know, Lake Austin, which to me is a river, but you guys can do what you want with that. Leave to you guys. It's not like some rivers I've seen. So is the flow there, it's smooth, it looks pretty smooth. After rain, it's maybe more bubbly. Is it laminar? What makes something laminar? Yes,
Something is like a parabolic flow.
say again.
A parabolic flow.
Parabolic flow.
Within the vessel.
Anything else you want to say about laminar flow?
So that's streamlined.
Streamlined, yeah. So okay, what happens in blood vessels? Well, there's let me show you some pieces. These are just some images from actual papers, so you don't necessarily need to interpret all of them. But okay, so blood flow is it can become close to laminar in some of the smaller arterioles, the very small vessels, but it's pulsatile, so it's not truly smooth, as you said, right? The velocity profiles are not, it's not continuous, right? The other aspect is that there's interactions with the wall of the blood vessel, right, which we really don't take into account. We're talking about laminar flow. So we're not talking about a rigid, unchanging vessel wall, so there's some interactions there. The other, oh here, let me show you okay, and the other big property that I wanted to point out that Facil's law is actually for a Newtonian fluid versus a non-Newtonian fluid. So blood is not really a Newtonian fluid. A Newtonian fluid is uniform. Blood is not actually so uniform. We can approximate it as a uniform fluid, but it's not really. And so we can talk more about that property as well. So we saw pulsatile flow, blood flow, especially as we get into some of the larger vessels, is turbulent. There are regions of turbulence, right? Maybe not bubbles, but definitely turbulence. So there are some fluctuations in the flow, and that is especially pronounced under certain conditions. When flow rate increases, those turbulent patterns increase. You may have heard of Reynolds number. Has anybody heard that or used it in your research? Okay, a few of you, yes. So that's a ratio that tells us about fluid inertial forces compared with viscous forces. So here we're obviously seeing some impact of changes in flow, and as well as viscosity and local differences in vessel diameter that make a difference. You don't need to remember this, but just to remember, if you've dealt in Reynolds numbers before, low Reynolds number is where you see conditions of laminar flow, right? And high Reynolds number is where we see turbulent flow. Here's just some, one thing we haven't really talked about. So turbulence can come at, obviously if there's a site where you have a plaque, right, that's a place where you're going to see some turbulence, for sure. But turbulence also comes in at, this would be probably better if I enlarged it, but at connections. So when a larger vessel goes into a smaller vessel, we never really talked about that structure, how does it look? But at that point, there can be some local, regional turbulent flow, or at least definitely not smooth flow. And these are some models that were produced by a research group that was trying to improve grafting, so vascular grafting for limb or digit replacement. And these are some models that they generated to look at these connection points where you have two vessels coming together, and you get what's called an anastomosis. Is really just a word for the connection. But at that point, you get some disrupted flow. It's hard to predict the flow, the blood flow pattern at that point. So it's clearly really a deviation from our ideal case. And let's see, I wanted to also show you this a bit more detail about Newtonian fluid, which is the idealized case that we think of with Lucille's law, where, so in a Newtonian fluid, it's we said it's uniform. In addition, the shear stress of that fluid is proportional to its strain rate. Can someone expand for us, what is the strain rate? What's that refer to?
Velocity gradient.
Say again?
Velocity gradient.
Velocity gradient. Well, what's strain?
The proportion of how much it stretches.
Say again?
The proportion of how much it stretches.
Yeah, it's deformation. It's the stretch. It's deformation that's happening. And here we're talking about how much deformation do you get in response to applying that stress, right? So for a Newtonian fluid in laminar flow, we'll talk about some perfect conditions. The shear stress, it turns out, is proportional to the strain rate, and the viscosity is a constant. So you see this relationship between shear stress and strain rate is very much linear, goes through the origin, and the rate of change in that deformation is constant over time, right? So for a non-Newtonian fluid, this and I don't know if I said it, but the constant of proportionality here is in fact the viscosity, right? So the slope here gives us viscosity. For a non-Newtonian fluid, that relationship kind of breaks down. So shear stress and shear rate, they're no longer simply linear. In fact, they can have a time-dependent relationship. So the amount of deformation that you get may change based on the history of the system, how much stress has been applied previously, right? So that's a situation that's obviously much more complicated. Here are some, you can peruse these when you have free time. You can see how different hemocrit values, going from, say, 40 up to 60, so I don't know if you can see the symbols very much, but going from this squares up to triangles increases, so we increase viscosity, we said before, and you can see that this relationship for actual blood is not so linear. What other parameters do they have on here? They also show you hemocrit staying constant, but fibrinogen, which is one of those clotting proteins that we mentioned very early in the class, changing. So lack of fibrinogen, viscosity decreases, and you can also see that here. Actually decreases down to a more Newtonian-like fluid. So I think, yes?
Oh, so shear rate and strain rate is the same thing, just to make sure.
Shear rate and strain, so the strain rate is how much deformation do you get for an amount of applied stress.
Okay. Versus shear rate?
And shear rate is, so the change in shear over time. Yeah, so those are going to be the same for a Newtonian fluid, which I think is what I just asked. So this is, I'm not going to dwell too much on that, but just to say that the ideal case is not all there is out there. And some of you may work in labs that are really focused on cardiovascular modeling. Has anybody worked in the SACS group and just worked with some of these parameters? So it can generate some really sophisticated real-life deviations from actual flow conditions. Okay, and then this is another study where you can see another deviation from the ideal case is the fact that the veins are really a bit collapsible, as we said, based on pressure from the surrounding tissue. So this is something that's not captured in such a simple, the simple state of the law, but that here this is a model where it tries to capture how does venous flow rely on venous pressure, and how does the wall pressure actually get into a regime where it can be negative wall pressure and the vein can start to collapse in on itself. That is why I said in the beginning we're really going to think more about arterioles instead of veins as an ideal case for talking about Poiseuille's law relationships. I'm actually wrapping up what I have planned for today. Sorry that we didn't go the whole time. Hopefully some of you can start your vacations if you're getting on the road. I want to remind you this is the reading, how it looks for the rest of the semester, post-Thanksgiving. We already talked about this. We're going to talk about Chapter 16 and Exam 3. Let's see, there is someone who is going to take the exam early. You might want to come talk to me at the end of this class, so we can arrange that. Are there any questions about material or logistics? All right, I'm sorry I didn't go the whole time today. Don't hold it against me. I should have added more. Okay, have a great Thanksgiving, everybody.